Calculated inflow provides the sum of all inflows into a reservoir, including gauged inflows and ungauged inflows. Gauged inflows are measured at river gauges built on major rivers or tributaries. A map of Roosevelt Lake shows gauged inflows at Tonto Creek and the Salt River. Every other water flow into Roosevelt Lake is an ungauged flow. Calculated inflow is determined based on spillway flow and lake elevation, which are recorded over a period of time. Using the knowledge of spillway flow and the change in lake elevation over time, we can calculate the total inflow into the lake. This calculation is made without the use of any gauged inflow data. A simple starting point for calculating inflows is a reservoir which has a constant elevation through time and a known spillway flow. In this example, the lake elevation is not changing. You can see that the calculated inflow must be equal to the spillway outflow. Spillway outflow is a known quantity, and so the unknown inflow is equal to the spillway outflow. Calculating inflows requires on-working knowledge of net area contents tables. The volume of any lake is available in the table for that reservoir. At each lake elevation, this table provides the corresponding area in acres and volume in acre-feet. If you know the surface area of a lake at any elevation, then you also know the volume of water 1 foot deep at that elevation. Based on 1 foot increments and interpolation, the net area contents table provides the total volume of the lake at each elevation. Now let's determine the unknown inflow when the lake elevation changes over time. The spillway gates have been closed and the lake rises 1 foot over a period of 1 hour. When a lake elevation has changed over a period of time, the CFS flow rate can be calculated. This change in reservoir volume over time in units of acre-feet per hour can be converted into units of cubic feet per second using the basic equation and solving for CFS. We have shown that a changing lake elevation can be used to calculate the unknown inflow into a lake with closed spillway gates and no water passing through the turbines. What if the lake elevation rises 1 foot in 1 hour and the spillway is releasing 20,000 CFS? What is the unknown inflow? The spillway release and the lake volume change will be used to determine the unknown inflow. The spillway release in CFS will be added to the inflow represented by the change in lake volume over time. Both of these flow rates will be added together when the lake rises. The lake is rising 1 foot while the spillway flow is 20,000 CFS. The unknown inflow is 20,000 CFS, which accounts for the spillway discharge, added to 11,500 CFS, which accounts for the lake volume increase. The unknown inflow has now become the calculated inflow and is 31,500 CFS. When the spillway is flowing and the lake is rising, the unknown inflow is equal to the spillway outflow plus the flow determined from the volume change in the lake. When the reservoir is falling with the spillway gates open, you can see that the spillway flow must be greater than the unknown inflow. To calculate the unknown inflow in this case, start with the spillway flow and then subtract the flow represented by the volume change over time in the lake. If a spillway flow is 20,000 CFS and the lake falls 1 foot in 1 hour, what is the unknown inflow? The inflow represented by the change in lake elevation over time will be subtracted from the inflow represented by the flow through the spillway. The unknown inflow is 20,000 CFS, which accounts for the spillway discharge, minus 11,500 CFS, which accounts for the lake volume decrease. The calculated inflow is 8,500 CFS. When the spillway is flowing and the lake is falling, the unknown inflow is equal to the spillway outflow minus the flow determined from the volume change in the lake. Understanding calculated inflows provides a foundation for understanding flood operations at dams. Several examples reinforce the significance of calculated inflows. Number 1. Hydrograph and other data is more meaningful to a person who understands that calculated inflow includes both gauged and ungauged inflow. This hydrograph from 1980 shows gauged and calculated inflows. Note that the calculated inflows are labeled gauged and ungauged. A second example. Understanding calculated inflow provides an intuitive grasp of the meaning of changing lake elevations as large spillway outflows are occurring during a flood. This intuitive feel helps in understanding the WEROC reservoir trends and prioritizing action among reservoirs. Number 3. Calculated inflow provides information available to a dam tender during a total communication or data failure, or when spillway operational priorities leave no time to communicate with WEROC. The dam tender is trained to determine calculated inflows on an hourly schedule during critical flood events by manually measuring lake elevations and spillway releases. By knowing calculated inflows during a storm, the dam tender is in a position to manage the reservoir independently when required. During some emergency spillway operations, the dam tender may not have time for any calculations, and the overall understanding of calculated inflow leads to operational principles which can be applied to manage the spillway and reservoir during a flood. In the absence of communications, or when there is no time to communicate with WEROC, the dam tender will operate by using 5 basic principles. These principles may also provide a useful guide for operations in WEROC during the peak inflow hours of extreme flood events. Number 1. Never let water overtop a spillway gate. Number 2. Pick a target elevation, usually 4 or 5 feet from full lake, that is desired at the end of the flood event. Number 3. If the water surface in the lake is rising toward the target elevation, increase the spillway gate opening until the lake stops rising. Number 4. If the water surface of the lake is going down, away from the target elevation, decrease the spillway gate opening until the lake stops falling. Number 5. Continue to attempt communications with WEROC when possible. Your understanding of calculated inflows and use of the basic water equation used to convert CFS to acre-feet is vital to WEROC operations. Now it's time to practice what-if problems to reinforce your skills.